Welcome to this session. In this video, I will discuss a problem on solution to the differential equations. The statement is given by the system is described by the differential equation. So double derivative of y of t plus 3 into derivative of y of t plus 2y of t equals to 4 into e power minus 2t. With initial conditions y of 0 equals to 3 and y derivative of 0 equals to 4. So find the total response of the system, 0 state response of the system and 0 input response of the system. So now first we try to transform this differential equation into S domain. Thereby the equation seems to be an algebraic equation. Then we try to find the response of the system. So first we will find the total response of a system. So we transform the equation into S domain using differentiation property. So before that, so we try to write in the differentiation from for the given equation. So that becomes d square by dt square y of t plus 3 into d by dt of y of t plus 2 into y of t equals to 4 into e power minus 2t. Now we need to transform this into S domain. So for that we use differentiation property. Using differentiation property, in time domain, so we write, so d square by dt square y of t. Suppose we recall the differentiation property. So if y of t is the time domain signal, then its Laplace transform will be y of s. Suppose derivative of y of t is there, then its Laplace transform will be s into y of s minus y of 0. So double derivative d square by dt square y of t. So then its Laplace transform will be s square y of s minus s into y of 0 minus d by dt of y of 0. Now we use this property to convert the differential equation into S domain. So here the first term becomes s square y of s minus s into y of 0 minus d by dt of y of 0 plus second term 3 into s y of s minus y of 0 plus 2 into y of s. So equals to, so Laplace transform of e power minus 8 is Laplace transform of e power minus 80 equals to 1 by s plus a. So e power minus 2t we can write it as 1 by s plus 2. So 4 is there. So 4 by s plus. So this we name it as equation 1 because we use this equation in the further case also. So here neglect the initial, we use the initial condition to find the total response of a system. So we substitute the initial condition s square y of s minus y of 0 is 3, so it becomes 3s minus, so derivative of y of 0 is 4, so we can write 4 here, plus 3 s y of s minus 3 into 3, so that becomes 9, plus 2 into y of s equals to 4 by s plus 2. Now we further simplify this equation to get the response of a system as, so we take y of s is common from the terms, so y of s is there in the three terms, so we take y of s is common, so and we can write it as s square plus 3s plus 2 minus 3s minus 4 minus 9, it is minus 13 equals to 4 divided by s plus. So we further simplified y of s into s square plus 3s plus 2 equals to, we shift these two terms to the right side, so this becomes 3s plus 13 plus 4 by s plus y of s into s square plus 3s plus 2 equals to, so here after simplification we'll get 3s square plus 19s plus 30 divided by s plus. So now we write y of s here, y of s equals to 3s square plus 19s plus 30 divided by s square plus 3s plus 2 into s plus. Now this is the quadratic equation, we can write into simple poles form as s plus 1 into s plus 2. So that is 3s square plus 19s plus 30 in the numerator, and denominator part becomes s plus 1 into s plus 2. Again s plus 2 is there, so we can write s plus 2 whole square. So this is y of s. Now we use partial fraction expansion to find the time response of a system. So using partial fraction expansion, y of s equals to 3s square plus 19s plus 30 divided by s plus 1 into s plus 2 square equals to, so we write a by s plus 1 plus b by s plus 2. There are repeated poles here, so we can take one more term, c divided by s plus 2 square. So now we take LCM on right side, so 3s square plus 19s plus 30 divided by s plus 1 into s plus 2 square equals to, so LCM is s plus 1 into s plus 2 square, so we write a into s plus 2 square plus b into s plus 1 into s plus 2 plus c into s plus 1. Now the denominator on both sides becomes cancelled, then the equation remains is three s square plus 19s plus 30 equals to a into s plus 2 square plus b into s plus 1 into s plus 2 plus c into s plus 1. Now put s is equal to minus 1 to get a value. So a value, so we'll get here 14. Then put s is equal to minus 2. So we'll get c is equal to minus 4. Similarly, if we compare s square coefficients on both sides, s square coefficients on both sides, so we'll get a plus b is equal to 3. Then we need b value, so b value is equal to minus 11. Now we'll substitute these equations, these values of a, b, c in the equation. So we'll get y of s is equal to, therefore y of s equals to, a value is 14, so 14 by s plus 1, plus b value is minus 11, so minus 11 by s plus 2, and c is minus 4, so we write minus 4 by s plus 2 square. Now to get the time domain response, so we use inversion of this Laplace transform here. So apply the inverse Laplace transform, so we'll get the time domain response of a system. Apply inverse Laplace transform on both sides. So here we'll get y of t equals to 14 into 1 by s plus a. So this is e power minus at. So in position of here we have 1, so t, minus 11 into, again it is 1 by s plus a, so this is e power minus at, so now it is e power minus 2t, minus 4 into, so 1 by s plus a square, so that gives t into e power minus at. So these all the signals represents the right sided sequence are causal signals, so then we multiply with u of t. So Laplace transform of 1 by s plus a equals to e power minus at, and similarly Laplace transform of 1 by s plus a square is equal to t into e power minus 8. Now this is the total response of a system. This gives total response of a system. So now we'll move to the second part, B. So B is zero state response. Zero state response. While finding the zero state response, so we say that we name it as Y zero state response, ZS of T. So we need to find zero state response. So in zero state response, so we assume all initial conditions are zeros. So all initial conditions are zeros, or we neglect the initial conditions. So because zero state response indicates that this is the response of a system when it is in resting position. So now from equation 1, so by neglecting the initial conditions, we'll get s square plus 3s y of s plus 2 into y of s equals to 4 by s plus 2. So neglecting initial condition means y of 0 is 0 and derivative of y of 0 is equal to 0, or this we can also say that y dash of 0. So now y of s into s square plus 3s plus 2 equals to 4 by s plus. So therefore y of s equals to 4 by s square plus 3s plus 2 into s plus. So that equals to 4 divided by. So we convert this quadratic equation into simple poles form. So this gives s plus 1 into s plus 2, again s plus 2, that gives s plus 2 whole square. Now use the partial fraction expansion. Using partial fraction expansion, so y of s equals to 4 by s plus 1 into s plus 2 square. So that is a by s plus 1 plus b by s plus 2 plus c by s plus 2 square. Now we will find ABC as we did in previous case, and we try to find the zero state response. So we take LCM on right side as we did in this case, and after simplification, so we'll get A is equal to 4 and B is equal to minus 4 and C is equal to minus 4. So by keeping the length of video in mind, so I just directly taken this value A, B, C. So to find this value, follow the procedure what we did in first case. So we'll get these values. Then y of s becomes y of s equals to 4 by s plus 1 minus 4 by s plus 2 minus 4 by s plus 2 square. So apply the inverse Laplace transform. So to get the time response, so that is zero state response, y z s of, and this is y z s. So y z s of t, z s indicates zero state response. So 4 into e power minus t minus 4 into e power minus 2t minus 4 into e power t into e power minus 2t, and this is the causal signal, so into u of t. So this gives the zero state response of a system. Similarly, the third one, so we find the third bit, zero input response. Zero input response. So here input is 0. So we consider the initial conditions and the input becomes 0. So from equation 1, so we can write s square y of s minus. So we consider the initial conditions here, but input becomes 0. So s square plus 3s y of s plus 2 into y of s equals to 3s plus 30. So right side part, that is 4 by s plus 2, that becomes 0 because that is nothing but input, so that it becomes 0. So now y of s we can take is common here, so s square plus 3s plus 2 equals to 3s plus 30. So y of s equals to 3s plus 13 divided by s square plus 3s plus 2. So that using partial fraction, so we can divide it as a by, so this is s plus 1 into s plus 2, so we can write s plus 1 here plus b by s plus, so simply we use y of s equals to, so 3s plus 13 divided by s plus 1 into s plus 2 equals to a by s plus 1 plus b by s plus 2. So finding a value and b value, so as following the procedure, so we'll get a value is a is equal to, so after simplifying, we get a is 10 and b is equal to minus 7. So y of s equals to 10 divided by s plus 1 minus 7 divided by s plus 2. So apply the inverse Laplace transform. So we get y of t, or we can call 0 input response zi of s, y zi of t equals to 10 into e power minus t minus 7 into e power minus 2t, and this is the causal signal, so we can write u of t. So this gives the 0 input response of a system, 0 input response of a system. So this is all about this problem. So y zi of s, 0 input response. Here for cross checking purpose, so we can also use the total response y of s is equals to the sum of the two response zs of t and zi of t. So we can also cross check it. So total response y of s, total response y of s equals to 0 state response plus 0 input response, or in time domain, so we can write it as y of t equals to y zs of t plus y zi of t. Thank you.